Hello friends. This video is a continuation of my last one, where I shared how I put together a stereoscopic camera using two ESP32 camera boards serially connected to each other, and one of them in turn being connected through a serial interface to a PC running some Python code controlling everything and allowing the capture of corresponding left and right images of any scene. My objective was to do some experimentation with distance or range finding using the camera, and today I'll share some early work I've done. What you're looking at now is my test setup, where I fixed the camera to a stand and have used a strip of painter's tape with some markings approximately every 30 centimeters from the camera that runs along my table. I'm using a small foam egg as the object of interest that we'll be taking pictures of, mounted on a mini tripod. I've got the Python code running on a laptop connected to the camera, and I capture images with the egg at distances of approximately 60, 90, 120, and 150 centimeters from the camera. I'll show you each set of left-right images as we go here. First for 60 centimeters distance. Second for 90 centimeters. Third for 120 centimeters. And finally for 150 centimeters. Now, before I go through the results, I need to provide a little theoretical background about how we go about determining distance from stereoscopic images. Here's a simplified diagram of the stereo capture setup we've got. It's a bird's eye view, so imagine you're looking at it from directly above. We have the left and right camera sensors below here, and we have a point P in three-dimensional space that we're taking a picture of. These cameras are assumed to be parallel to each other and aligned in the Y plane. Because of this, we can simply ignore the Y dimension, and we can only deal with X and Z coordinates, where big Z here is the distance from the camera. And so you can think of point P projecting its image to a corresponding point on each image sensor. On the left to XL, and on the right to XR. Keep in mind XL and XR are local coordinates relative to the center of their corresponding sensors. These projection lines from point P go through the optical center for each sensor on the left and on the right, that I denote CL and CR. The distance D is the length between those optical centers. And we should note that the center of D corresponds to x equals 0 in the coordinate system of point P. The focal length of the camera is F. With all this information, we can use the disparity of where that projected point lands on each sensor to determine the distance that P is from the camera using some simple geometry. So on the left side, you can see a right angle triangle being formed by XL, optical center CL, and the center of the sensor. Corresponding to that, you can see another larger right angled triangle being formed by CL, point P itself, and the green point here. We can see similar triangles being formed on the right side as well. right? We can now use the principle of similar triangles on these to figure out z. And I'll show the math for that. The end result is distance z equals df divided by xl minus xr. Now we can apply this to the images we capture to see if we're able to manually calculate the distance of the egg from the camera. Let's look at a side-by-side of the images captured at 60 centimeters distance. I'm just using Microsoft Paint to find corresponding points in the images. I'll start by finding the pixel coordinates at the center of the egg for each side. For the x coordinate on the left, we can see about 198, and for the right, about 131. Note that the y coordinate between each is off by about 7 pixels or so. That violates our assumption about the cameras being aligned in that plane. To be honest, there are a lot of issues with my DIY stereo camera. First, the PCB prototyping strip board I use to mount the components on is awfully thin and super flexible, and so care needs to be taken to minimize how much it bends horizontally. So there's a good chance these cameras were not all that parallel to each other. Needless to say, my camera is not exactly a precision instrument, but I figured for my tinkering purposes, it would be okay. Also note that our image resolution is 320 by 240. On the sensor local axis, we'll treat the coordinate of 160 pixels as the center of the image. Thus, for an x coordinate of 198, we'll actually use positive 38 pixels in our distance calculations. And for the x coordinate of 131, we'll use minus or negative 29 in our calculations. Next, let's take a look at the left and right images from the 150 centimeter distance step. I've got about 189 for the x coordinate on the left and 149 for the right. Okay, one more thing to look at before revealing the results. Remember how in our calculations we're using actual distance units like millimeters and centimeters, but from the images so far we only have pixel units. How do we convert that into actual distance measurements we can use in our calculations? Let's crack it open the datasheet for the camera module that's connected to the ESP32 cam board we're using. That's the OmniVision OV2640. We take a look at the pixel size specification, and we have each pixel with a 2 micron width and height. So if we're dealing with the full available resolution of the sensor, approximately 1600 by 1200, we would just multiply our pixel coordinates by 2 microns to get the equivalent distance on the sensor. And if you take a closer look at the datasheet contents, you'll see that multiplying 2.2 microns by the maximum pixel resolution of the camera, it corresponds to the image area specification. Okay, that's enough of that. Let's get to the actual calculations and results. I've gathered all the information we've collected in a spreadsheet so we can automate these calculations. First, we have our actual image resolution specs of 320 by 240. We need to convert this into actual distance measurements based on our sensor pixel size. But remember, we're mapping that 320 by 240 over the entire image sensor area, which actually covers about 1600 pixels by 1200 pixels. So we need to scale our pixel size accordingly. So our effective pixel size is 11 microns. So that's scaled from 2.2 in the datasheet to 11. We've got our focal length of 3.6 millimeters that we know from referring to documentation available with a camera board. And we've got our baseline distance, which is the distance between optical centers. I measured as best I could between the centers of the camera lenses using digital calipers and got 85.8 millimeters. And we have a list of the X-pixel coordinates for the center of the egg for each set of images taken at the various distances from the camera. So this spreadsheet applies the distance calculation that we derived with all of this information. And we can see from the results that we're really off by quite a bit. What was supposed to be a 60 centimeter distance comes out at about 42 centimeters. And the 90 centimeter distance image comes out at 54 centimeters. And it gets worse as we progress. Now, I wasn't completely distraught with this. We do at least see that the computed distance does increase. So at minimum, we can tell if objects are further or closer, even if we can't tell exactly how far. So from a tinkering perspective, it was somewhat successful. And if you look up the topic of stereoscopic distance mapping, you'll see a lot of information about how the camera setup needs to be calibrated. And there's a lot of fancy transformations that can be applied to do that. Still, I thought that we'd get better results than this. I don't necessarily need super accurate distance measurements, just something that's roughly accurate. That would, maybe get me to within 5 centimeters or so. But then I noticed something as I played around with the X-pixel offsets. If I apply an offset of minus 22 pixels to the left image coordinates, as I just did there, we get computed distances that are actually very close to the expected values. And so without any fancy calibration, we're able to get what I consider fairly decent results, right? So 62 centimeters, about 94, 122, and 156. Certainly, we'd want to apply a better procedure than this in most real applications, but for my purposes, it does validate the approach, and I'm quite satisfied for now. There are many improvements I can make to the camera, including properly mounting the sensors to a more precisely fabricated, rigid mounting surface. I can also apply calibration methods and image rectification to optimize the accuracy of our results. And eventually, we can apply some computer vision techniques to compute the disparity and distance maps for all points on the image. The result would be a 3D map of the objects we're scanning. Really, there's lots of possibilities. Anyway, that's all for now. I hope you found this interesting or at least informative. Until next time, keep tinkering.